In this video lecture, we shall learn the Stark effect in rotational spectra. The Stark effect is the shifting and splitting of spectral lines of atoms and molecules due to the presence of an external electric field. The amount of splitting and/or shifting is called the Stark splitting or Stark shift. It is the electric field analog of the Zeeman effect, in which a spectral line is split into several components due to the presence of magnetic field. The rotational Stark effect is the splitting of molecular rotational energy levels in the presence of external electric field. The Stark effect can be observed in both emission and absorption lines. The Stark effect can be used to determine the dipole moment direction in a molecule. However, the Stark effect does not provide the signs of the dipole moments. It was discovered by Johann Stark in the year 1913. Stark observed the effect in the hydrogen spectrum by creating a strong electric field in a space of a few millimeters. Stark effect is of fundamental importance in the analysis of rotational spectra. Stark effect is the splitting of a spectral line in the presence of an electric field. The rotational lines may be shifted as well as splitted. The Stark effect can be used to determine the dipole moment direction in a molecule. However, the Stark effect does not provide the signs of the dipole components. In the present context, it is a splitting of rotational absorption line into various components which are subjected to electric field of several hundred volts per centimeter. That is, the MG/MJ degeneracy of the energy levels is lifted by the electric field. Consider a rotating linear molecule with angular momentum perpendicular to the electric field. The field tends to twist the dipole and gives a faster rotation when the dipole is oriented in the direction of the field and a slower rotation when it is opposite to the field. The minor difference between the dipoles pointing in two directions causes the splitting of energy levels. The direction of resulting angular momentum may be along the electric field or may oppose it. So this is the direction of the electric field. We are going to consider this is the direction of the external electric field. Suppose if the dipole element is along the electric field, then this will have a faster rotation. So the figure shows a faster rotation. Suppose if the dipole is opposite to the external field, then this will have a slow rotation. Here the splitting of energy level arises due to the interaction of electric field and the component of dipole of a molecule. Any rotational energy level splits according to their degeneracy. Stark effect can be classified into two categories: first order Stark effect and second order Stark effect. First order Stark effect goes like this. If the dipole moment mu has a component along the angular momentum j, the first order Stark effect is observed. That is, mu is parallel to j. In this effect, the splitting of rotational energy is directly proportional to the electric field. That is, mu is directly proportional to the electric field. First order Stark effect is exhibiting in symmetric of molecules, for example, ammonia, methyl chloride, and so on. Here, IA is not equal to IB, which is equal to IC. The shifting of rotational frequency is given as del nu is directly proportional to mu E. Second order Stark effect. If the dipole moment mu is perpendicular to the angular momentum, mu is perpendicular to j, then the second order Stark effect is observed. Here, mu is directly proportional to E squared. Linear molecules exhibit the second order Stark effect. Carbon monoxide, carbon dioxide, and so on. And here, IA equals 0 and IB equals IC. The shifting of rotational frequency, that is, del nu is directly proportional to mu E whole squared. Thus, the first order Stark effect is linear in the applied electric field, while the second order Stark effect is quadratic in the field. Now we shall discuss in detail about the Stark effect. So we are going to discuss the Stark effect on linear molecules as well as the spherical top molecules. Consider a molecule having an electric dipole moment mu placed in an electric field X. Usually, the electric field will be denoted as E, but here we are going to discuss often E as rotational energy, eigenvalue of the rotation energy. That's the reason that the electric field is denoted as capital X here. In the presence of the field X, the interaction energy of the dipole is expressed as H prime, which is equal to minus mu times X. H prime is the perturbed Hamiltonian. So the total Hamiltonian is nothing but unperturbed Hamiltonian plus perturbed Hamiltonian, which is given as equation 1.92. That is, H equals as rotational energy of a linear molecule or a spherical top molecule plus the perturbed Hamiltonian, which is given as mu times X. The Stark term minus mu times X is generally small and can be treated as a small perturbation on the rigid rotor. If the electric field is taken along the z-axis, then the perturbed Hamiltonian is given as minus mu z times X. For linear and symmetric rotor molecules, it is easy to evaluate the effect of perturbation H prime on the rigid rotor levels with the appropriate basis. So one basis JKM basis, and this is for symmetric top molecules, and Jm is a joint eigenstate with the J and M, which is the basis function for the linear molecules. Here, K is the top axis quantum number. For linear molecules, there will be no top axis quantum number. We have only top axis quantum number J, K, M, joint eigenstates, all the three quantum numbers, which are the base for symmetric top molecules. Perturbation calculation shows that there is no first order correction to the energy for linear molecules. So we are not going to discuss the first order correction for linear molecule. However, for symmetric rotor, the first order correction gives. So E first order correction for the symmetric rotor, which is equal to minus mu mj times kx divided by j into j plus 1. Hence, for symmetric top molecules, so we are going to discuss now the Stark effect for the symmetric top molecules. Hence, for symmetric top molecules, the energy eigenvalue is given as, we know that E total equals E rotation energy plus the E first order correction energy. So which is given as equation 1.95. So E, J, K, Mj, which depends on all the three quantum numbers J, K and Mj, which is equal to BHC J times J plus 1 plus A minus B HC K squared minus mu K Mj X divided by J into J plus 1. Here J equals 0, 1, 2 and K goes from 0 plus or minus 1 plus or minus 2 up to plus or minus J. K depends on J. Whereas Mj equals 0 plus or minus 1 plus or minus 2 up to plus or minus J. The selection rule goes like this. Selection rule is del J equals plus or minus 1, del K equals 0 and del Mj equals 0. Now when the transition goes from J to J plus 1 and K will have a transition K to K and Mj also will have a transition from Mj to Mj. That is, when J goes from J to J plus 1, K will go from K to K and Mj also will be the same thing. The first order correction energy for the symmetric top molecules. So we are going to calculate the Stark effect for the symmetric top molecules. So this is the equation 1.97 says about for J and equation 1.98 for J plus 1. So you just substitute instead of J, you substitute J plus 1 here. You will get equation 1.98 and this expression for J plus 1 and this expression for J. So we are going to calculate the transition from J to J plus 1. Okay, this is a correction energy. So now change in correction energy. Change in correction energy is nothing but equation 1.98 minus equation 1.97. So which is equal to the change in correction energy del E1, which is equal to this expression minus this expression. So we have this expression, minus of minus will give us plus, so plus mu mj kx divided by j into j plus 1. Now just take the LCM, we will get the change in correction energy is given as equation 1.100. Now the selection tool del j equals plus 1 and del k equals 0, del j equal to plus or minus 1, del k equals 0 and del mj equals 0 gives the first order correction energy to the transition frequencies. Now del E, the first order correction del E is nothing but, which you have already seen this equation earlier. Here J is the rotational quantum number and K is the top axis quantum number. Thus the change in second order correction frequency. So this is the expression for energy. If we divide by H, that will give us the change in second order correction frequency. So which is equal to 2 mu x kmj divided by, so you are going to divide this one as H. The value of H is nothing but 6.626 10 power minus 34. Now 1 divided by 6.626 in 10 power minus 34 will give us 1.509 in 10 power 33. That is equation 1.101. Now we are going to change the unit. Usually the dipole moment will be measured in terms of dB, whereas the electric field will be measured in terms of volt per centimeter. But here it is volt per meter, whereas mu is there. So we are going to change the unit now for dipole moment and the electric field. 1 dB equals 3.336 in 10 power minus 30 coulomb meter. And you just substitute here. So that will give us 1.509 multiplied by 10 to the power 33, which is nothing but 1 by H multiplied by the conversion of dB, which is equal to 3.336 in 10 power minus 30 multiplied by 2 mu. So now this mu becomes in terms of dB. So x times k mj. But here x is nothing but volt per meter. So we have to convert this one volt per centimeter. So for that, what we can do is we just multiply by 10 power 2. So that will give us 0.5035 mu x. Now this x is volt per centimeter. This mu is measured in terms of dB. But earlier, here x is measured in terms of volt per meter. So we have changed it into 10 power minus 2. We have multiplied with 10 power minus 2. That will give us 0.5035 d mu times x multiplied by 2k mj divided by j into j plus 2 in terms of megahertz. See here, del mu 1 is nothing but measured in terms of megahertz. So this is equation 1.102. So this is the final one. So we have obtained the expression for change in second order correction frequency. So which is nothing but given by equation 1.103. So here del mu 1, which is nothing but mu 1 minus mu 0, where mu 0 is the unperturbed frequency, mu 1 is the first order correction frequency, and del mu is expressed in terms of megahertz. Mu is measured in dB and x is measured in volt per centimeter. In the absence of field, a single line results for j equal to 1, k equal to 1, to j equal to 2, k equal to 1 transition, which we see now in the figure. And when the electric field is applied, j equal to 1 will transform into j equal to 2. So there will be a transition from j equal to 1 to j equal to 2 when you are going to apply electric field. So this j equal to 2, k equal to 1 will split into 5 levels. Using the formula do j plus 1. So instead of j you substitute 2. So 2 times 2, that will give you 4, 4 plus 1, so 5 levels. So we are going to see the figure now. And also there will be 3 transition lines will be observed in the first order spectrum as per del mj equals 0, which is as shown in the figure in the next slide. Their frequencies can easily be obtained by using equation 1.103. So this is what I said. When there is no electric field, the transition will take place j equal to 1, k equal to 1 to j equal to 2, k equals 1. And this excited level, when you're going to apply the electric field, that will split into 5 levels according to the formula 2j plus 1. So 2j plus 1 will give us 5 levels. So this will split into mj, which goes from minus 2 to plus 2 through 0. So minus 2, minus 1, 0, 1, 2. So there will be 5 levels. What is j equal to 1, k equal to 1? According to the formula, again 2j plus 1, this will split into 3 levels, minus 1, 0, and 1. What is the transition now? Between these two levels, we have transition. And transition will take place according to this expression, 1.103. According to this expression, del mu 1. And of course, del mu 1 equals mu 1 minus mu bar. You bring this mu bar this side, we will have mu bar plus. So this is what it is given as mu bar plus. And here it is mu bar minus. And it is central line is mu naught. See, this is mu naught plus this expression, and mu naught minus this expression, and there will be mu naught. And what is the transition? Transition will take place according to this selection rule, del mj equals 0. So this is 1 to 1, del mj equal to 0, and from 0 to 0, again del mj equal to 0, and from minus 1 to minus 1, del mj equal to 0, according to this transition selection rule. So this figure shows that the first order Stark effect of a symmetric of molecules for j equal to 1, k equal to 1, to j equal to 2, k equal to 1 transition. Now we shall discuss for the linear molecules. So we are going to discuss the second order rotational energy levels and second order correction for linear molecules, and thereby we are going to draw some pictures using selection rules. So for the transition levels. For linear molecules, k equals 0 levels of symmetric rotors, the first order correction reduces to, so there will be no first order correction for the linear molecule. And hence one has to investigate the second order terms. In such cases, the correction to the energy level is given by this expression. So this is second order correction for the linear molecules. Second order correction is directly proportional to mu x whole square. So it's given as exactly equation 1.104. Now, we know that the expression for the rotational energy of a linear molecule without perturbation is given by this expression. We know already, we have studied already earlier, 1.105. Now, the total energy, expression for the total rotational energy of a linear molecule with the perturbation is given as E equals E rotational plus the correction energy. So this is unperturbed and this is perturbed. And this is unperturbed expression for the energy, rotation energy, and this is expression for the correction, second order correction. Now, this is in the presence of, in the absence of electric field, and this is in the presence of electric field. Now we are going to use the selection rule as it is, del j equals plus or minus 1, del mj equal to 0, j comma mj goes to j plus 1 comma mj. And this is level is 0 comma 0, this is 1 to 0, and the first 0 stands for j and second one stands for mj, and this will be j plus 1, so this will become 1, and mj equals 0 here. Now we'll have to use same equation 1.104. The second order correction is given by this expression. Now, as I said just now, this refers j and this refers mj, and we are going to have the correction change in rotation, change in second order correction, which is given as this minus this, that is E102 minus E002. We are going to calculate the transition between these two lines. We are going to calculate. Now let us calculate now. So first point is your mj equals 0 here. You substitute mj equal to 0 here. So when mj equal to 0, this will become 0. This term will become 0. When this term becomes 0, the term will be j into j plus 1 divided by j into j plus 1, 2j minus 1, 2j plus 3. And this term will get cancelled. The remaining term will be 2j minus 1 multiplied by 2j plus 3 in the denominator. Now you substitute another j equal to 0 here. The first condition goes like this: j equals 0 and mj equals 0. So when j equals 0, this becomes minus 1. When j equal to 0, this becomes plus 3. So plus 3 multiplied by minus 1 give you 1 divided by 3 with a minus sign. So this is what is given here. See, E002 is given as mu square x square divided by 2hb multiplied by minus 1 by 3. Of course, b is a rotational constant. B is nothing but rotational constant. So which is given as minus mu squared x squared divided by 6hb, equation 1.108. And this is the expression for the second order correction energy for j equals 0, mj equals 0. Now let us calculate the second order correction for j equals 1, mj equals 0. Again you substitute mj squared equals 0, we will have j into j plus 1 divided by j times j plus 1, 2j minus 1, 2j plus 3, and this term and this term will get cancelled. The remaining term will be 2j minus 1, 2j plus 3. You substitute j equals 1 and this becomes 1 and this will become 2 plus 3, 5. So 5 multiplied by 1, so 1 by 5 we'll have. So 1 by 5. So we have mu squared x squared divided by 2hp multiplied by 1 by 5. So the second order correction for j equals 1, mj equals 0 is given as mu squared x squared divided by 10hp. Now you have to subtract. So this minus this will give us change in second order correction energy. So this minus this, as I said. So j, there's a mistake here, it is 2. This is not 1, this is 2. So E, j plus 1, 2, and here it is E, j, m, this is 2. It is not first order correction, this is second order correction. So there's a mistake here, we have to correct it. And so we can subtract. Let us subtract this term expression for this term is given by this, and this term is given by this. Now take the LCM, you will get 8 divided by 30. 8 divided by 30 can be written as 8 divided by 15 multiplied by 2. And 2b is nothing but mu naught, which you already studied earlier. So this expression becomes, that is the change in second order correction energy is given by 8 divided by 15 mu square x square divided by h mu naught. Now change in second order correction frequency is given by, and this expression divided by h will give us this expression. So our h will become h squared here. And of course we know that del nu second order, which is nothing but nu second order minus mu naught, where mu naught is the unperturbed frequency. So nu2 equals mu naught plus 8 divided by 15 mu squared x squared divided by h squared mu naught. Now look at the expression now. Del nu square, that is second order correction, del nu second order correction is equal to, so this mu will have to change into dB, x will have to change into volt per centimeter as we have done already earlier, and 8 divided by 15. So taking into all these things will give us 0.1352 mu squared x squared divided by mu naught. So the second order change in second order correction frequency is given as 0.1352 mu squared x squared divided by mu naught in terms of megahertz. Here mu is expressed in terms of dB and x is expressed in terms of volt per centimeter. Now look at the transition line. So this is a Stark effect of j equals 0 to j equals 1 transition for a linear molecule. So in the absence we have in the absence of electric field, we have j equals 0, 0, mj equal to 0. So 0, 0 to 1, 0. So this is referred as S. Whereas here we have, and this line j equal to 1, this line is split into 3 lines here according to 2j plus 1. So we have 2j plus 1, which is nothing but minus 1, 0, 1. And what are the transition? Use the selection rule del mj equals 0. So we have only one line. So transition goes from 0 to 0. So we have only one line, which is nothing but mu naught plus a divided by 15 mu squared x squared divided by h squared mu naught. The importance of Stark effect studies is listed below. The Stark pattern, if well resolved, can be used to identify the involved J value in the transition. The intensity distribution of the Stark pattern helps us to distinguish the lines of P, which is nothing but del J minus 1, what we call this as P branch, and Q del J equals 0, what we call this as Q branch, and R branch, which is nothing but del J equals plus 1, branches of the spectrum. A measurement of the Stark components gives a method for the accurate determination of electric dipole moment, which is one of the most important electronic properties of a molecule. The classical dielectric constant measurement also gives the dipole moment. However, there's a difference between the two methods. The obtained classical value is a complicated average of the dipole moments of the collection of molecules in all the vibrational states, whereas the microwave Stark effect allows measurement of the dipole moment of a molecule in a particular vibration state. In addition, the microwave method gives some idea about the orientation of mu in the molecule.